Greetings, my name is Dylan, and today I will be giving a summary on the document, the Google File System, which was published by Google in 2003. At the time, Google was rapidly expanding and needed a storage system capable of handling enormous amounts of data across thousands of inexpensive computers. Traditional file systems were not designed for this scale, so Google created its own distributed file system. The main goals of GFS were scalability, fault tolerance, high performance, and reliability, all while using commodity hardware instead of expensive enterprise servers. This paper explains the assumptions behind GFS, its architecture, how it handles failures, as well as the performance results achieved in real deployments. The authors begin by explaining that Google's workloads are very different from those assumed by traditional file systems. Firstly, hardware failures are expected rather than the exception because thousands of inexpensive machines are constantly running. Second, Google works with extremely large files, often several gigabytes or even terabytes in size. Third, files are usually written once by appending data rather than repeatedly modified. Finally, Google's applications prioritize high throughput over low latency because they process massive data sets instead of serving individual interactive requests. These observations shaped every design decision made in GFS. GFS uses a relatively simple architecture consisting of three major components. The first component is the master server, which stores all metadata such as file names, directory structure, chunk locations, and replication information. The second component is the chunk servers. Instead of storing complete files, GFS divides files into fixed-size chunks of 64 megabytes. These chunks are stored across many chunk servers, and each chunk is replicated 3 times by default to improve reliability. The final component is the client. Clients communicate with the master only to obtain metadata. Once they know where the data is stored, they communicate directly with the chunk servers for reading and writing. This prevents the master from becoming a performance bottleneck. GFS introduces several design features that distinguish it from traditional file systems. One important feature is the use of large 64 megabyte chunks. Larger chunks reduce communication with the master and improve sequential read and write performance. Another feature is metadata stored entirely in memory. Because metadata is relatively small compared to the actual data, storing it in RAM allows the master to respond very quickly. Finally, the operation log records every metadata change. This log is replicated across multiple machines so the master can recover quickly after failures. When a client wants to read data, it first contacts the master to determine which chunk servers contain a desired chunk. After receiving that information, the client communicates directly with one of the chunk servers, bypassing the master for actual data transfer. Writing data is a bit more complex. One replica is chosen as the primary. The primary determines the order of all the write requests and forwards those writes to the secondary replicas. This guarantees that every replica processes writes in the same order. This approach maintains consistency while keeping the master out of the data path. Fault tolerance is one of the paper's most important contributions. Since hardware failures are expected, every chunk is stored on multiple machines. The system consistently monitors chunk servers using heartbeat messages. If a chunk server fails, the master automatically creates new replicas from healthy copies. GFS also uses checksums to detect data corruption during reads. If corruption is detected, another replica is used while the damaged copy is replaced automatically. These mechanisms allow GFS to recover from failures without the administrator intervention. The authors evaluated GFS using both benchmark tests and production clusters. They found that read performance scaled well as more clients accessed the system simultaneously. Write performance was somewhat lower than expected because of network limitations, but the aggregate throughput remained very high. Perhaps more importantly, real Google clusters stored hundreds of terabytes of data across hundreds of chunk servers while serving hundreds of clients simultaneously. These results demonstrated that GFS successfully met Google's storage requirements. The paper highlights several strengths of GFS. Its simple, centralized design makes management easy. Replication provides strong fault tolerance. Large chunk sizes improve throughput for sequential workloads. However, there are also limitations. Having a single master introduces a potential single point of failure, although replicated logs and shadow masters reduce this risk. The system is also optimized for large sequential files rather than workloads involving many small files or random writes. GFS had an enormous influence on modern cloud computing. Its ideas inspired several open-source distributed storage systems, including Hadoop Distributed File System, or HDFS. Many concepts introduced in this paper, such as replication, chunk-based storage, centralized metadata management, and fault tolerance using commodity hardware, remain common in today's distributed storage platforms. Although Google's internal systems have evolved beyond GFS, its architecture continues to influence cloud storage technologies. In conclusion, the Google file system functionality changed how large-scale distributed storage systems are designed. Instead of assuming reliable hardware, it assumes failures will occur and automatically recovers from them. Instead of optimizing for small files and low latency, it focuses on massive datasets and high throughput. By combining chunk replication, centralized metadata management, large chunk sizes, and automatic recovery, Google created a storage system capable of supporting web-scale applications. Many of these design principles continue to influence distributed storage systems used throughout the cloud computing industry today. And then here's my reference, and thank you very much for listening.